Good morning to anyone. First, I would like to thank Anny and the Collège de France for this invitation. I would like also to acknowledge contributions to this talk from my colleagues. The outline of my presentation is as follows. First, I will briefly review how sea level has been measured over the past century. Then I will highlight the importance of vertical land movements at the coast through a couple of examples. And I will show how the GPS can provide a solution to monitoring vertical land movements. I will show you some recent results, and I will discuss the limitations and uncertainties of these results. Well, according to David Cartwright, a UK scientist, in his Tides, A Scientific Story, the first available records of sea level were performed in 1679 with a tide pole, as pictured here. The first automatic recording tide gauge is credited to Henry Palmer in 1831. Well, I will not enter into the details of these techniques, but underscore that whichever the technology, the tide gauges are measuring the sea surface height with respect to the ground upon which they are grounded. No. Only for the past 2 decades, we have sea level observations from satellites with centimeter level precision in a terrestrial reference frame whose origin is naturally the center of mass of the Earth around which any satellite orbits. Consequently, the bulk of evidence for global sea level rise comes from tide gauge records, including the latest study from Church and White. And it is also important to note that most studies, if not all recent, are based upon the same data set of worldwide tide gauge records assembled by the Permanent Service for Mean Sea Level. Well, the maps here shows the selection from Church and White. This selection was based on the tide gauge records having at least 60 months, that is 5 years, over a decade. An interesting exercise was carried out by Douglas, who computed the acceleration term of sea level change from the PSMSL tide gauge records and plotted these results with respect to the record length. There is, as you can see, a large dispersion in the shortest records, which is mainly due to interannual and decadal oscillations caused by oceanic processes, a wide range of such oceanic processes coupled with atmosphere and so on. Douglas, based on this graph, concluded that at least a minimum of 60 years are required to derive climate-related signals from a tide gauge record. And you can see the reason why here. He also noted that the trends are mostly linear, whichever the underlying process. Now, computing the trends, the linear trends of these same tide gauge records does not show a dramatic reduction in the dispersion, as you can see, at least not as dramatic as for the acceleration term. The reason is that there are natural reasons of spatial variability of the rates of sea level change coming from the climate signals, as has been shown by the previous speakers, from the land ice melting and from the thermal expansion. But there is also, and likely the largest source of spatial variability in the rates of sea level change from tide gauges coming from the vertical land motion. And I will show this through a couple of examples. The first one, in the top picture here, you can see remains of an electricity pole along a road constructed in 1975 in the area nearby Thessaloniki in Greece. The coastal plain of Thessaloniki is subject to a major, substantial subsidence process, as can be seen in these maps extracted from Psimolis and colleagues, which are yielding to subsidence rates of several centimeters per year, which is very large. This picture comes from the analysis of synthetic aperture radar images from satellites in an interferometric approach over the past 20 years, and still confirms that the rates of subsidence are of about 4 centimeters per year, and locally can reach 10 centimeters per year. These are aggravated by groundwater extraction in the 1970s, which stopped in the 1980s. But still, the sedimentation over the millennia timescale is continuing acting in this region. In this second example, the opposite situation can be observed at Vasa in Finland. The glacial hydrostatic adjustment model predicts an uplift of 8 to 9 millimeters per year. This uplift is in very well agreement with independent observation from the GPS technique, here shown over the last decade or so, which is really in very good agreement. So consequently, if one would like to project sea level towards the 21st century, the vertical movement has to be taken into account, as it was done by Keima in 2008. And we can see that by the end of the 21st century, the sea surface with respect to the land will reach a level similar to the end of the 1990s. Well, as a matter of fact, there is a wide range of geological processes that can cause spatial variability in the rates of sea level change from tide gauge records, as is very well illustrated here in this view graph. Two approaches have been used to correct for vertical movement at tide gauges. On the one hand, modeling. Unfortunately, there is only one geological process for which we have precise enough predictions, namely the GIA, which was presented formerly by Giorgio Spada. On the other hand, measuring through space geodetic techniques. However, the issue is challenging. We are aiming at rates of sea level change of the order of 2 millimeters per year, which means that the standard errors should be 1 order of magnitude less to be useful in this application and long-term trend sea level studies. Well, measure if one can. Indeed, 20 years have passed since the expression of the idea and the review of the candidate techniques, and the first results published with GPS in 2007. The GPS has appeared as the most effective technique, even though the other techniques are important in order to realize an accurate and stable terrestrial reference frame. So many lessons had to be learned in the GPS data acquisition, for instance, continuously instead of in campaign mode, and progress to be made in the processing of the GPS data. For instance, a key issue was, or is, the processing of the GPS data in a global network of stations. This is mandatory in order to compute precise orbits of the satellites, but also in order to accurately realize or align the results in the most stable terrestrial reference frame. And this requires an international infrastructure that is provided today by the International GNSS service. The other key issue is that the data has to be analyzed in a homogeneous way. That is, with the same models, the same analysis strategy, the same corrections. If there is any change in a model or a correction, all the data has to be reanalyzed to achieve these challenging vertical velocities that we are aiming at here. So it needs considerable computing capabilities. So in this slide is shown our latest GPS solution. The red arrows represent positive vertical velocities or uplift, and the negative vertical velocities are in blue and represent subsidence. Some known or expected patterns can be seen in this map. For instance, in the Northern Europe, which is a region affected by the GIA. So how well do these vertical velocities work when applying for the tide gauges? So this slide is an update from the previous one shown by Professor Stammer. In 3 different regions, namely the Northern Europe, Northwestern America, and also the Gulf of Mexico. Here are shown the annual time series and rates of sea level change, and it can be seen that within each region, nearby tide gauges are displaying quite different rates of sea level change. So here it is corrected by predictions from a GIA model, and we can see that in the regions dominated by this process, we perform a reduction of the dispersion in the rates of sea level change. But in other regions that are affected not only by GIA, like in Northwestern America, but also by tectonics, the models, of course, do not perform as well. And in regions far away from the previously glaciated areas, like in the Gulf of Mexico, there is little improvement in the scatter of this dispersion. And the last panels on the right side are the GPS-corrected tide gauge records with our latest solution. And we were pleased to see that this dispersion is reduced to 0.3 millimeter per year in these 3 regions. Well, I will just focus here briefly on the Gulf of Mexico and at the Grand Isle tide gauge record, which is showing a dramatic rise in sea level of about 1 centimeter per year, which means similar to what Professor Bart showed us for the last, for the deglaciation era, 8,000–10,000 years ago. And most of this rate of sea level change can be explained by the vertical land movement subsidence that is observed at Grand Isle. Here 2 images that show to have a sense of what it means 1 centimeter per year elevation in sea level. This is a picture taken in 1932, and here is the same picture taken in 2011, which gives a sense of what it means in terms of coastal impacts. On the regional scale, here we use the virtual station technique from Yevayeva and colleagues to build regional sea level curves. Here on the left panel, there was no correction with GPS velocity, and here on the right panel, data was corrected with GPS velocities. And there is a clear reduction in the dispersion again among regions from 1.2 millimeter per year dispersion here without GPS correction to 0.5 millimeter per year. And if we look at the individual records, this dispersion reduces from 2.2 millimeter per year to 0.5 millimeter per year. So we don't expect that to further reduce this dispersion because there are natural causes of variability, spatial variability in the long-term rates of sea level change that have been shown by the previous speakers from the land melting of ice, but also from the thermal expansion of the oceans. However, the use of GPS at tide gauges has still a certain number of issues that I would like to comment here. Not the least is the limited data availability that is illustrated here in the tide gauge network from the Global Sea Level Observing System program under the auspices of the UNESCO. And the white symbols represent stations that do not have yet any GPS stations at the tide gauge. And the purple-blue one are stations for which we could locate a GPS station in the vicinity, but this station was installed for other applications and the data is not available to the scientific community. In addition, there are 2 working hypotheses that should be kept in mind. The first one is that the GPS antenna is sensing the same movement as the tide gauge, which can be the case like here in Saint-Jean-de-Luz, but often there is a distance between the GPS antenna and the tide gauge. So we are assuming that the differential movement between both is the same. Like here in Brest, there is 300 meters distance between the location of the GPS antenna and the tie gauge record. Usually, it is a reasonable assumption, but in our case, it's necessary to have it. And the second one is that the land movements are linear of the tie gauge record length. Okay. Also, if we wish to derive robust vertical velocities that are representative of vertical land movements, a minimum length of continuing GPS should be collected. And this minimum length should take into account the noise in the GPS position time series. So typically today, we need about 8 to 10 years in order to get a reliable vertical velocity with GPS. However, this is average figures, of course. In particular, at the local scale, we are dependent on the choice of the equipment, on the immediate environment of the station, and the data access of this station. And here in the Venice GPS station, you can see that the GPS position time series is quite noisy, likely due to the equipment changes, but also the immediate urban environment. And the velocity that we estimated is doubtful, a positive uplift of 1.4 millimeter per year in Venice. Well, but actually, looking into the literature, and in particular results from the interferometry synthetic aperture radar from satellites, we found this map showing ground deformation relative to a point that is supposed to be stable. And what we could see here is that the GPS station is located in a place where actually there is an uplift of about 1 millimeter per year. So perhaps our GPS estimate, despite its noise, might be real. And the tie gauge station is located here, where with an independent method, using altimetry data and tie gauge data, we estimate that the velocity, vertical velocity, is about -1 millimeter per year, also in agreement with this result from Tosi et al. Well, recently, joining these various techniques, we addressed the case study of Alexandria. Alexandria was ranked 11 in terms of population exposure to coastal flooding by 2070, assuming a vertical land motion of 7 millimeter per year subsidence, because Alexandria is located near a delta. However, our results, previously published here, altimeter minus tie gauge or GPS, reveal very moderate subsidence, if any, at Alexandria. And we expanded with colleagues from the BRGM within the Cecile project these results using interferometry from radar images. And here you can see the results. Here are the tie gauge, here are the GPS, here's the scale. And we look at the scatters around each station. We found results in very well agreement with the independent techniques here. Well, to conclude, vertical land movements are a very important source of spatial variability in the rates of sea level change from tie gauge records. And today we have demonstrated that worth results can be obtained from the analysis of GPS data. These results should be expanded to other stations, more generalized, in order to detect fingerprints of climate-related signals. There is a technical need, I would say, to supplement the GPS data with these interferometry synthetic aperture radar images from satellites and its advanced approach, which is called PSE, for permanent scatter INSAR, which provides two informations. First, if the GPS station distant to the tie gauge is sensing the same movement. And the second one is that the GPS position is a point-wise information, and we need to spatially extend this, and we can achieve this with such techniques. Well, a key issue, I would say, I am perhaps repeating myself, is to develop and continuing observing this tie gauge network by supplementing the tie gauges with GPS stations at the tie gauge, if possible, or nearby, and also supplement this with INSA techniques. Well, I will not comment the last issue, which is very technical about the terrestrial reference frame, but if there are questions, I will be happy to answer them. So thank you for your attention.